in discussing space weather, that's only part of the sort of solar terrestrial interactions that occur. It's the most obvious thing because you have coronal mass ejections, you big blobs of plasma that slam into Earth's magnetosphere to go around the Earth, a lot of it, but a lot of it depresses the magnetic field, the whole geomagnetic storms, radiation storms, and so forth. But that's only part of the thing. These radiation storms actually have an interesting impact. And some years ago, back in the around 2000 or so, read an interesting paper that was published that actually made an interesting correlation here. Right here you see a graph that shows different years, and the up and down line there is solar activity through the 20th century. And you notice the peaks, and on top are marked influenza pandemics. And you notice that there's frequently an influenza pandemic right close to solar peaks. And again, there was an influenza pandemic in the 1990s, and some of y'all might remember the swine flu outbreak that occurred about 15 years ago at the last solar peak. Now, this latest solar maximum, there wasn't really much. But the other thing that happened that is interesting is that pandemics of other viruses, for example, SARS and things like that, tend to occur near solar minimum. So it's interesting that radiation does seem to have an impact. Now, there's different kinds of radiation, as we're about to see. And the most obvious is the solar radiation storms. During a major solar flare, you get solar radiation. That obviously, we know radiation causes mutations, and that seems to be correlated with influenza mutations. And again, the biggest flares tend to occur near the peaks or on the backsides of the peaks of the. Again, we have all the geomagnetic effect of space flight, aircraft, electricity, communications. We already talked about all that. But something else that I want to bring up is that we also have radiation from deep space, what we call galactic cosmic rays. And the galactic cosmic rays result from particles, high energy particles from deep space outside the solar system running into the solar system and running into the planets. Now, one of the things that's interesting is that the cosmic rays are also influenced by the radiation from the sun. Now, the cosmic rays have what we call, we'll talk more about this later in the semester, primary cosmic rays, which are these particles from deep space that hit the atmosphere, and what happens is they slam into an atom in the upper atmosphere and blast particles down, and these particles rain down on us, and then some of them make it all the way to the ground. Most of them dissipate. They're very short-lived things before they make it to the ground. So the primary cosmic rays are the ones from deep space. They create a shower of secondary radiation. And again, we'll talk about this later. The secondary radiation actually peaks about between 30 and 40,000 feet above the ground. Well, that's where commercial airliners fly. And one of the interesting things that we've discovered is that the more solar activity, the more coronal mass ejections, the less the cosmic radiation, the deep space cosmic radiation. This is called the four-bush decrease. And so what happens is that we think that what's happening is the coronal mass ejections going out there actually provide a buffer between us and the deep space radiation. Now, the deep space radiation is an entirely different kind of particulate radiation than the solar radiation. So more solar activity means more solar radiation. Less solar activity, conversely, means an increase in cosmic rays. Now, how does that affect us? Well, the most obvious effect is that the cosmic rays, when they hit nitrogen in the atmosphere, they transmute it. They actually cause one of the protons in the nitrogen to end up turning into a neutron. Don't worry about the processes, don't worry about that. It happens. But it's kind of the reverse of the process that's in the proton-proton chain that happens in the sun. But that makes carbon that has 6 protons, and instead of 6 neutrons, it has 8 neutrons. That's radioactive, has a half-life of several thousand years. And so what happens is that over time, this effect of producing carbon-14 in the atmosphere. Now what happens? You create carbon-14 in the atmosphere. The carbon-14 is radioactive, but it has a half-life of thousands of years, so it doesn't go away right away. It's going to end up bonding with oxygen, carbon dioxide. Well, that means some of the carbon and some of the carbon dioxide that's out there is radioactive. The carbon dioxide is then taken up in plants. Well, the plants keep the carbon, release the oxygen. That makes the plants radioactive. And then, then you eat a plant. So you eat a salad. You're eating radioactive plants. No way around that. A cow eats grass that's radioactive grass, so now you have a radioactive cow. Okay, and then you grind up the cow, and that makes burgers radioactive. Okay, so now the thing about this though is that this carbon-14 is interfered with when the wind particles come in and you get a coronal mass ejection. That interferes with some of these deep cosmic rays, and you end up getting less carbon-14. So one thing that you can do is dig up something that's been dead for a while, and generally what happens is when you die, you quit eating and breathing, unless maybe you're a zombie or a vampire. But if you quit eating and breathing, that means that you no longer are maintaining a carbon-14 balance. As long as you are alive, as a human being, you are taking in radioactive carbon in what you eat, and you're expelling this radioactive carbon and CO2 when you breathe out. So you're maintaining a constant balance. You're constantly the same level of radioactivity until you die. When you die, then what happens is you're no longer maintaining this balance, and because carbon-14 is radioactive and it does actually go back into nitrogen, it decays, gives off a beta particle and becomes a nitrogen-14 again, which is neutral. So as it decays, then you become less and less radioactive. So you can dig up something and find out how radioactive it is. Well, assuming that you have a constant level of C14 in the atmosphere, you can actually use this for radiocarbon dating. So something died at some time in the past, you dig it up, and you can see how radioactive it is. We're assuming if carbon-14 is produced by the same levels in the atmosphere, then by seeing how radioactive it is, you can figure out how long ago it died. So you can have human artifacts and say, oh, wait, this campfire was from 14,000 years ago, or this particular artifact that someone finds somewhere is from 11,000 years ago, or from 1,000 years ago, or from 1,500 years ago. So you do radiocarbon dating this way. But we do know that the solar output affects the carbon-14 production a little bit, not by a lot, but a little bit, which means that if you know exactly how old something is, I mean, there's a tombstone. You know when this person was buried. You know when the tomb was constructed. You know when someone cut down a tree and made a table out of it. Okay, so you know the actual date it quit living and quit maintaining its C14 balance. So all you have to do is do radiocarbon dating. If the dating comes up slightly younger than you expect, that means that there's a little bit more C14 in it, which means that the sun was slightly less active than normal. If, on the other hand, you get a date slightly older than it really is, that means it has less C14 than you expect, therefore the sun was slightly more active. Okay, so that means that this is one mechanism whereby, for example, that at solar minimum, you get a different kind of radiation which can affect other organisms. Well, when we go backwards, we find out that sure enough, during the Maunder minimum, when the sun was less active, we had less C14, or we had more C14 produced right there. Okay, and so we had more C14 produced here, and this is the graph is actually backwards. Less is at the top, hence the minus sign, and positive, so down is more. Okay, so again, astronomy way of graphing stuff. Okay, we find though, interestingly enough, that there was a period of time here in which the sun was also less active, and this was back hundreds of years ago in the Middle Ages. But then also way back during medieval times, there was a period of time, between 800-900 years ago, 700-800-900 years ago, the sun was very active right there. Even back around 1000 to 1100 or even 1200 years ago, the sun was very active. And so at that time, when the sun was very, very active, this was about the time the Vikings were crossing the North Atlantic in open boats. Not just because they're big, tough guys, but because the weather was nicer. So this actually corresponds when the sun is less active. We know at the Maunder minimum that we have colder weather. Conversely, when the sun is more active, it was warmer. During this period of time, they lived in thatched roof buildings in England because it was warm and balmy, climate, which it definitely is not now. Okay, so again, climate changes are tied to solar activity. At least this is how it's been for a very long time, and we can run backwards in time here for thousands of years and find there's a correlation there. Up until recently. Up until recently, things have changed. Again, we've got solar activity up, down, and so forth. Most of the 20th century was trending upwards. Right towards the end of the 20th century, it started this downward trend, which is continuing into now. Okay, so again, our next solar cycle is probably going to be another wimpy one, but we've been dropping for the last several solar cycles, and our last solar cycle we just finished up was an incredibly wimpy one. And so the 24th solar cycle was really wimpy. It's some of the wimpiest we've seen since, beginning of the 20th century, for a long time. If you look at National Weather Service data, climatological data for the DFW area, then the coldest winters were in the 19 teens and thereabouts during this period of time when the sun was less active, like it is now. We're not having super cold winters. So something else is impacting the climate other than the sun. What would that be? Well, a prime suspect would be human activity. So here we have a graphic that shows the standard temperature increase, here. Solar activity was increasing, but now it's decreasing again. But about the time it's decreasing, our CO2 or other greenhouse gas production has been increasing. And when the greenhouse gases, what they do is they hold in heat from the sun. And so that suggests that we have transitioned from a period in which the sun drove the climate to where we're driving the climate. Now, that doesn't mean the sun has no impact, because very famously, the rate of temperature increase has slowed down here in the last 15, 20 years or so. But you expect that, you actually expect it to be dropping, not just slowing down, because of the drop in solar activity. So at least it's just slowing down a little bit. So what does all that mean? Well, what we can say is global warming, or that topic, is way more complicated than most people make it out to be. There's probably more than one factor involved, human factor as well as the sun factor. And right now we're transitioning from solar-driven to human-driven climate change.